All right, so today we are talking about integration with substitution. So yesterday we sort of introduced that where we have some sort of complicated integrand and we're trying to take the antiderivative of that. And normally what we found is that if we come up with some helpful u and then take the derivative of that, then that can be used to substitute in for our integrand and our dx term, and then we can simplify it down, so to speak, integrate it, and then substitute it back into whatever that complex thing was. Okay? So yesterday, pretty much every problem that we looked at were polynomials of some type. Today, first thing we're going to look at are some trig problems. Not sure why that's not working there. I'll just keep doing it. We're going to look at some trig substitution, not trig substitution, but trig integration with substitution of trig problems. Trig substitution is actually a thing, okay, and another type of substitution or whatever. And then we'll look at some weird problems on the back that require a couple extra steps. Okay, so just if you remember, all of this is designed to give you some different tools to try to solve these integral problems. All right. Oh my word! Can we not start with something so that would look a little bit better? All right. So let's look at number 2. Number 2 says the integral of negative 20 sine of 5x times cosine cubed of 5x dx. Now I'm going to put some parentheses around this to make it a little bit more clear. In fact, I'm going to even rewrite this here. I'll say negative 20 sine of 5x. And then y'all remember that cube right there, that 3, what that technically means is cosine of 5x, and that whole entire quantity is cubed. So I kind of like to write it in this fashion just because it makes it a little bit more obvious, especially when we're doing our u substitution. Now, one of the things that we noticed yesterday with our u substitution is that normally, somehow, somewhere, we had 2 parts of our integrand, and one of them was like the derivative of the other. Okay? Another sort of hint or tip was normally if we had something which was raised to a power, then it was normally a pretty good idea to make that thing that was inside the parentheses with the power, to make that thing our u. Okay? Those are sort of like tips. Those aren't necessarily hard and fast rules, but those are sort of observations. If we apply that to this problem, which is a good idea, we would have u equal cosine of 5x. We are rolling, right? All right. Okay, let's go ahead and play the game. Next step, derivative of both sides. So d over dx equals, now let's remember, derivative of cosine is negative sine, that's right. Negative sine. But this is not just any regular old sine, this is sine of 5x. So we have to apply the chain rule here. So the derivative then of the inside would be 5. Okay? Then our next step in the process was to multiply both sides by dx. So we have du equals, and I'm going to move this 5 as a coefficient up front here. So negative 5 sine of 5x dx. All right. So if we go over here now and look and see what we can substitute, we've got the cosine 5x. We're going to replace that with a u, so that's u cubed. The dx we've got accounted for right here. The sine of 5x we've got accounted for right here. But notice my multiplier here is a negative 5, and my multiplier there is a negative 20. So what did we do in situations like that yesterday?
Multiply.
Yeah, figure out what you need to multiply. In this case, it's going to be by 4. So multiply that side by 4, multiply this side by 4, and I get 4 du equals negative 20 sine 5x dx. Now, it's at the front office, right?
Yep.
Alright. So, great, we can replace, now we've got the negative 20 taken care of as well. We're going to replace all of that with 4 du. Now, if we want to, I can line it up. 4 du. And remember the constant multiple rule of doing integrals. If we wanted to, we could pull that 4 out and then just have the integral u cubed du. So we've effectively simplified that complex integrand into something a little more basic. We now just take the antiderivative. So power up that 3, so that's going to be a 4. We'll divide that by 4. My 4 up here really looks like a u, so I'll make it more clearly a 4. Plus c. That's kind of good. That's kind of nice. So those 4's cancel. Substituting back in this, and I could write this if I wanted to as bracket cosine 5x 4 plus c, or if we wanted to write it in that fancy way, cosine to the 4th 5x plus c. James, how could we check and verify that this is the correct answer?
Take the derivative.
Take the derivative of it. Let's do that real quick. Derivative of cosine to the 4th 5x would be 4 times, that is cosine cubed of 5x, right? Times derivative of that inside of that was the 3rd, so derivative of cosine is negative sine 5x times, chain rule, derivative of the inside, 5. Negative 4 times, 4 times a negative times a 5 is negative 20. And then we have sine 5x and cosine cubed 5x, which matches our original integrand. Okay, so a pretty good way of verifying that's right. We'll leave that up for Harley. Let's, why don't you all go ahead and give number 3 a shot. Probably got the rest of that copy down there for you. James, do you have any idea what we should do for a cotangent or for a u?
U is cotangent To the fifth, 4x.
So du over dx would be what, James?
Cosecant squared 4x.
Not quite.
Negative cosecant squared 4x.
Get closer.
Oh yeah, times 4.
Okay, times 4. Getting there, but here's the issue. This is cotangent to the fifth, right?
Oh
Which
yeah.
that would mean that would mean that, right? Okay. Well, that kind of changes things significantly. So just to be clear here, James is suggesting that we use cotangent to the fifth, 4x be our u substitution value. Okay. So I think we have to do the chain rule. Agreed? Okay. So we'll pop down the 5. So 5 times cotangent of 4x to the 4th, right? And then what's the derivative of cotangent?
Cosecant squared, or negative cosecant squared.
Negative cosecant squared
4x times 4
times 4. Okay, I'll multiply both sides, make sure I'm in the frame here. Both sides by dx, and I get du equal to see 4 times negative times 5. So negative 20 cosecant squared of 4x times cotangent of 4x to the 4th. Right? Times dx. Alright, now let's see what we've got here. So I can replace the cotangent to the fifth 4x with a u, and then I've got the dx taken care of right here. I've got the cosecant squared 4x taken care of right there. Now over here I have a negative 8, but here I have a negative 20.
Oh, no.
Okay, so what do I need to do? I need to turn this negative 20 into a negative 8. Any ideas?
Divide by 20 over 8.
Okay, divide by 20 over 8. And if y'all are hesitant on that, we can talk about it in a second. Before we do that though, the one last thing, I'm looking at this term right here, and I've got a cotangent 4x to the 4th, but there is no cotangent 4x to the 4th over here in the integrand. So I can't say that all of this can substitute that, because this term right here is not present in the integrand. It's sort of like I had a times tangent, and I'm like, I want to substitute all of this for all of that, but all of this is not a complete match for all of that. Does that make sense? Okay, so even if I can turn negative 20 and negative 8, which is I would suggest we totally can, I still I have to get rid of this term completely, okay? And you say, no big deal, just divide both sides by cotangent of 4x to the 4th. Does that make sense? Let me show you what that's going to end up with. We're going to end up with something like u times du divided by cotangent to the fourth of 4x, and then that's also times 20 over 8, or whatever. Anyway, the problem, or divided by, I guess it's 8 over 20. But anyway, the problem is that now I have u's and x's all mixed up together in this integrand, all right? And, well, I don't know how to take the integral of u divided by cotangent to the fourth 4x. I need something to be that's just like the integral of like u to the sixth, okay? I can't have u divided by this other. Does that make sense? And what's more, u is a function of x, and I also have like some other x's down here, and I'm doing du, which is it's just it's possible using the techniques that we've seen to do antiderivative when it's just you know, when this variable matches this variable. If we've got another variable down here which is dependent on that one, then all of our tools and tricks are out. Okay, we cannot do this. This is a dead end. All right. Unfortunately, we've got to figure out where we went wrong. Does anybody have any suggestions? James?
Could we not use C and use
Cosecant instead of cotangent? Possibly.
Wait, couldn't we just use like cotangent 4x?
I want to do her idea first. Okay. What's the derivative? Okay, so you want to say cosecant, right? What's the derivative of cosecant?
Is negative cosecant cotangent.
So that would be negative cosecant 4x cotangent 4x. So if I do cosecant 4x, that could take care of this guy. Okay? But then I would have, trying to find everything else here, okay? I would actually, what my du term would end up having would be a cosecant 4x and a cotangent 4x. So once again, I would end up with extra material that doesn't completely match it. Okay? So, good idea, but not quite. Really what we want is something that when we take the derivative of it, it's going to completely give one of the other terms. Ivan, what was your suggestion?
Cotangent 4x.
Okay, so instead of having our u be cotangent 4x to the fifth, he's suggesting have it just be cotangent 4x. Just the thing that's inside the parentheses. Very similar to the way that over here, our u was cosine 5x. It wasn't cosine 5x cubed. It was just this part right here, which was inside that term. You see how we did that? All right. Ivan, that is the correct path, and so that's what we're going to do, and I'm going to write over here. All right. I got to let you try some things, all right? That's otherwise just, you know, you hold your hand the whole time. All right, so let's try u equals cotangent of 4x. Now, if we do that, du over dx, call it out, Ivan.
I mean, it would be cosecant squared 4x times, it's actually negative cosecant 4x times 4.
Times 4. Are you okay if I put that 4 out in front then, just immediately kind of like all in one shot, because we're AP calculus students. Alright. Then, multiply both sides by dx. So du equals negative 4 cosecant squared of 4x dx. So the cotangent 4x I can replace with a u to the fifth. The dx and all of that. Okay, I've got a multiplier issue. Here I've got a -4, there I've got a -8. This also makes that multiplier thing a lot easier.
Mm-hmm.
Alright, what are we gonna multiply both sides by? 2. So, that's gonna give me 2 du equals the 2 times -4 gives things like that. Alright, this is pretty good. So that 2 is a constant multiple, so I can just pull that out. Antiderivative of u to the 5th is what class?
U to the 6 over 6.
Keep going. 2 over 6 reduces to 1/3, so I have u to the 6th over 3 plus c, which then I'm going to write that as 1/3 times u to the 6th, so I'll write that as cotangent to the 6th, 4x plus c. And Harley, you missed it, but how can we check to see if this is the right answer? Yeah. Okay. So, yeah, a little bit of a hint right there. If you've got one of these which has the larger term, like, I mean, this one you might have said, it might have been cosecant, and, you know, then this could have been u squared. But the thing is that we're going to take the derivative of it, and what we want is, and when we take the derivative, we want to make sure that the thing that's the derivative will end up effectively canceling out that other term. So it's normally in your best interest to put your u in whichever one of these has the higher power. All right. So seek the higher power. All right. Put the u there. I don't know if that's entirely consistent, but anyway. All right. Let's turn the page. Now, does anybody feel like expanding 2x plus 5 to the 5th?
Mm-mm.
Anybody want to FOIL that 5 times? Well, not 5 times, but you know. Anybody feel like Ivan says no. Maybe Roger does. Roger, you want to FOIL that out? 2x to the 5th, or 2x plus 5, 2x plus. Okay, yeah. All right. So this seems like a good candidate for a u substitution, right? Mm-hmm. And it seems like this is kind of like what we did yesterday. Mr. Guy, what the heck are you doing here? It's just, if this was like yesterday's problems, which I'm starting to get a bad feeling here, what would we say is equal to our u? 2x plus 5. Alright. And then we take the derivative. So du over dx is equal to 2. So du equals 2 dx. Okay. So I've got the 2x plus 5 can be replaced with a u to the 5th. Now I'll tell you a good way of dealing with this constant multiplier stuff like this. Just watch this. Just pull that 3 out, okay? Rather than dealing with divided by 3 halves and stuff like that, it's kind of a mess. Let's pull that 3 on the outside there. The advantage here is now all I have to worry about is what's the dx term. Okay? The 3's taken care of, check. This is taken care of, check. The dx, I'll take care of this. I'm going to solve this all by itself by dividing both sides by 2. So du over 2 equals dx. Got it? There's an x. And like I said a minute ago when we went through that whole example, you already heard my speech. You can't have a function and like the dependent term of that function. You can't have all in the same integrand, right? That we don't have the tools. We don't know how to solve that. So we need to get rid of that x. I'm not going to write it right there. But the thing is we can walk back up here to our very first step and we can solve this for x. Solve for x. This is another fun technique here. So we can subtract 5 from both sides. So we get u minus 5 equals 2x. And then divide both sides by 2, and we get x equals u minus 5 divided by 2. So now I have a way of substituting for that x. I can say, parentheses, u minus 5 divided by 2. Right there. Now, we've got some multipliers here. I have a 2 in the denominator, 2 in the denominator. That's going to be 4 in the denominator. I'm just going to want to pull that out here in front of the integrand so I don't have to mess with it. So I have 3 over 4 integral. Now this is not too bad to distribute that u to the 5th. So u to the 5th times a u is going to be a u to the 6th minus 5u to the 5th. So it's looking a little different than yesterday, but not too bad.
Where did we get the 3 over 4?
I have a fraction, 2 times 2 is 4, and if 4 is a dividing term, it's the same thing, so I just
Oh, okay.
I can pull that out front as a constant multiple. All right.
Why is there no 5 on u over 2? I thought it was u minus 5 over 2. And you just put the, like, okay, you see dx? We replace u minus 5 over 2 for x.
So there's the
Yeah.
So dx turns into
Yeah.
u minus 5 over 2. The 2x plus 5 to the 5th turns into u to the 5th. And the dx turns into u over 2. Did I miss a term? I don't think
wait, no, yeah. I had it written down, I just didn't see it.
Okay. Good, keep asking questions. Alright. I think we've got something that we can handle. That 3/4 is a multiplier out front, so I'm just going to leave that as 3/4. And let's go ahead and just take care of this. Antiderivative of u to the 6th is
u to the 7th over 7.
7th over 7 minus 5u
To the 6th over 6.
plus c. Alright, so I'm going to do two things at once, but I'm sure you can handle this. I'm going to distribute that 3/4, and I'm going to substitute in u. So a 3/4 times a 1/7 turns into 3 over 28. And instead of writing u to the 7th, I'm going to write 2x plus 5 to the 7th minus 3/4 times 5/6 is going to be 15 over 24. And instead of writing u to the 6th, I'm going to write 2x plus 5 to the 6th. And when I multiply 3/4 times a constant, I get another constant. So let's see here. Oh yeah. The 15 over 24 can be reduced, right, to 5 over 8. Okay, that's it. So we've got time for maybe doing a couple more of these problems. Does anybody have any question about this new u substitution? We in the frame there, James? Okay. So I call this u substitution solve for x. In fact, that's I think the title of the the lesson, right? So, sort of a little hint there about what you're gonna have to do. Alright, y'all pick one. 6 through 10.
Seven.
Alright. So integral 3x times x minus 4 to the negative 4. What do y'all think would be a good u value here? X minus 4 sounds good to me. So du over dx is not x. What's the derivative of x? And 1. So du equals dx. Good one, Adam. I'm gonna pull that 3 out in the front since I don't really want to mess with anything. That takes care of the 3. It also takes care of the dx. Dx is equal to du. That's also going to take care of the x minus 4. That's going to be u. Negative 4. What about that x?
You solve for it.
Let's solve for it. So u plus 4 equals x. Nice little dividing term there. Now what we'll do is we'll go ahead and distribute this u to the minus 4 times each of those. What is u to the minus 4 times u to the first?
U to the minus 3.
U to the minus 3. Remember, you multiplying same basis, you add the exponents. Negative 4 plus 1 is negative 3. Plus, this is just a multiplier, 4 u to the negative 4. Alright. I'm liking this. Constant multiple up front. 3. Bracket. Call it out to me, class. Antiderivative of u to the negative 3.
E to the negative 2 over negative 2.
Plus. Call it out. 4. Plus c. See, it always gets faster. Second time, third time. So now we'll just go ahead and distribute that 3. At the same time, we will rearrange these fractions and do substitution all in one shot. So here you go. I'm going to write that as negative 3 halves times x minus 4 to the negative 2 minus, now this 3 will cancel out that 3, and so all I have is going to be 4 in the numerator. And then, instead of writing u to the negative 3, I'm going to write x minus 4 to the negative 3 plus c. Actually, why not? Share the 3 with the c. Let's see what my answer key. Alright, so if you want to make this for fast grading in a couple of days, then anytime you have a negative exponent, you can always just shove that in the denominator. Now, this is my answer key. It's going to leave that. I'll shove this in the denominator. So it's going to say negative 3 over 2 times x minus 4 squared minus 4 over x minus 4 cubed plus c. So if you want to make it so it's easy to grade, then you go ahead and do that. And believe it or not, apparently, from what I've read, that's some of the reasons why we have rules for math, is so that it's easy to grade. Like, no negative exponents. Always put it in the denominator. Well, why? So it's easy, so we can grade easier, you know. And there's a lot of advantages to having negative exponents, because anytime you end up having any problem, especially if you're taking the derivative, you pretty much need to pull it up in the numerator so you have the negative exponent so you can apply the power rule or the anti-power rule, but whatever. I read one place where I was like, someone's like, why do we rationalize the denominator? You know what I mean? When you have like 1 over root 2. I'm like, I don't know. I looked it up. Best thing I could find, or that I did find, was that so it's easier to grade. Now, I mean, there are advantages. I mean, root 2 over 2, I mean, that's kind of a standard. But that's just standard because that's what everybody else does. But anyway. Alright, so there's your answer. If you want to, you can take the derivative, check your work. Does anybody have any questions on this? Feeling pretty good? Alright, let me give you the homework and also shorten it while I do. Seems to me like this is another good candidate for the odds only approach. How's that sound? That'll cut it down to only 8 homework problems. Yeah. Tell you what, let's cut it down even more. Let's go 1, 3, 5 on the front, 9, 11, 13 on the back. So just 6 problems. If you can do this 3 times and get it right, then I think you're good. 1 through 5 on the front, 9, 11, 13.
No.
So is this one the one we did right now? Is this due or is this just notes?
That's just notes. It says
Okay.
notes on the front.
Oh.
So yeah. I know we're not really in the habit of doing that, but that's what all my classes used to be. All my math classes. Do the notes in class and then here's the homework. Thanks for watching. James, go and kill it.